Hi folks, are you able to hear me?
Yes, sir.
Is it loud and clear? Is the microphone clear, or you need it to be even more clear?
Little low, sir. Volume is little low.
Okay, give me 2 minutes, I'll fix that. How is it now? Is it better? How is the volume now?
Yes, sir.
Is it better? Okay.
Yes, sir.
Okay, great. I think some of you wanted to have a discussion session. Yeah, please go ahead.
Yes, sir. I mean, I couldn't understand the noise apart from the switching, the switching watches, the noise contribution of the switching watches. I couldn't understand that part from the video lecture.
Okay, yeah. So that part was specifically left, unsaid. I didn't cover it fully. What I will do is I will have a separate lecture to, to probably cover that. Not today, but I will definitely cover it separately because that is going to require a lot of analysis. So most likely early next week, I'll do that. Okay. So either I will have a live class or I'll record it and put it up. One of the two I will do. Okay. That I know that it was not covered fully. And I will do it separately.
And sir, regarding that, while using LS for source degeneration, so we get a resistive real part, and to reduce it, I mean, we need a capacitive input resistance for the mixture so that we can have so that the Q of the output tank of LNA don't get reduced.
Okay.
So in order to omega t ls to reduce, so we reduce the value of ls or we reduce the value of gn.
Okay, 1 minute. You are talking about at the input of the mixer, right?
Yes.
You don't need ls at the input of the mixer unless you really need it. If it's inside the IC, you don't need it. So this is your LNA. Okay, if everything is inside the IC, okay, if everything is inside the IC, your mixer may look like this. You don't need an LS for the mixer as well. Okay, I've just shown like a single balance mixer, but here you don't need if it's on the same IC.
So for the linearity of the GM part, then so, I mean, I was thinking about if we have to do fix the linearity of the GM, then by using LS, and it also acts as as a filter so that the higher order harmonics and all those get filtered out. So in that
Actually,
case,
I still don't understand. 1 minute, just take a step back. So if you want to linearize the mixer, okay, so you have to, of course, if you're worried about the linearity of the GM itself, you have one control is control over the VGS minus VT.
Yes, sir.
Okay, so that is one option. So just give me a minute. So you can control. So basically set the current density of the mixer device. So that is definitely one possibility. The other possibility is to is of course to do either degeneration either resistive or inductive. You can do that. You can build a more linear transconductor. Okay, there are various ways of doing this. All of them will have an impact on Zn. If you do anything to the transconductor, it will no longer be capacitive, it will be Zn. Okay, if you have an inductor, the input will be resistive, right? If you have a
Yes,
resistor,
sir.
what will the input impedance be?
Omega T LS. I mean, sorry.
Basically, you get a response that is basically omega t by omega times whatever you have, right? So if you have a
Yes, sir.
resistive
Yes.
degeneration, what will you see at the gate? Omega t by omega times R. Isn't it?
Yes. Yes.
So what kind of impedance is that?
I mean, purely resistive impedance.
No, it's not. Okay, no, it's not. Please think about it. Zn will be omega t times R by omega. That is not purely resistive. That is frequency dependent.
Okay, so by omega, sir, that is capacitor.
Yeah, it will look like a capacitance. Okay, so that is a possibility if you can tolerate the capacitance. Okay, that will also linearize. These are the two most common ways. You can use more linear. There are, I think in earlier years I have covered very linear inductors that can be done at some point of time. Yes, but it should not be required for this course. I'll put it that way.
Okay, sir.
Yeah.
So instead of using LS, using a resistance is much more effective in that sense.
I don't know. Even a resistance may not be required, I think, but that's again.
Okay.
You go for the resistive degeneration if you don't get the requisite linearity from the basic GM by controlling VGS minus VT, right?
Okay, sir.
So you go for the resistive degeneration only if you're not able to. So I think at least for the project you will not need it, and in general for the general purpose circuit you will not need it.
Okay, sir.
Okay.
Sir, can you briefly explain about the full current steering part? Like the V naught should be at least root 2 times VGS minus VT. Like I didn't understand the part.
Oh, this is Hariharan.
Yes, sir.
So have you done the analog ICs course, or you're doing it? You're
Yeah,
doing
I'm
it.
doing it parallel.
You're doing it in parallel. Okay. So you remember the differential amplifier. So let us say this current was 2I naught. So so if I apply delta V here, right? So the bias currents will be I naught each, and there will be a signal current that will be Gm times delta V, correct?
Yes,
Is this
sir.
correct?
Yes, sir.
So in one transistor, it will be I naught plus Gm delta V. In the other transistor, it will be I naught minus Gm delta V. If I plot, I'm going to call the differential current. So sorry, it will be I naught plus Gm delta V by 2. In the other one, it will be I naught minus Gm delta V by 2. The total differential current is Gm delta V. Okay. So right, this is what it is. If I were to, this is the input differential voltage versus the output differential current. Okay, so if I were to plot one against the other, what kind of curve will I get? For small delta V's, it will be linear. The slope will be what?
GM by KGM.
It will be Gm. If I apply delta V at the input, the output differential current is GM delta V, isn't it?
Yes, sir.
So the slope will be GM. But if I start increasing delta V, what will happen? One side will get larger and larger current, other side will get smaller and smaller current, until if I apply a large enough delta V, so what will happen? I'll get 2 I naught and 0.
Yes, okay, sir.
Okay, so the maximum current for this system may be 2 I naught. Similarly, if I applied a large negative delta V, I'll basically get minus 2 I naught, right?
Yes, sir.
What will happen is that this will take some nonlinear. The actual characteristic as delta V becomes larger and larger will be nonlinear. This is the point that I'm asking you to find.
Okay.
Some so VA. So I'm asking you, what is VA? The curve is of course going to be symmetric. I'm asking you, what is VA? What is the value where the current just becomes 2 I naught or minus 2 I naught?
Yeah, okay.
Okay. And you can represent that in terms of VID. Okay. I mean, that is the VID. You can represent it in terms of the VD sats, not VID. You can represent it in terms of VD sat. VA is the VID. So this is basically VID at which and of course, if you increase delta V beyond that, nothing changes, right? I want to find out exactly where this happens. How do you do this? You know everything about the circuit, right? So now these are the large signal circuits. So you need to write down the equations. So you know that I1 plus I2, let the two currents be I1 and I2. I1 plus I2 is 2 I naught. This is one equation, right? What is the second equation you know?
The square law equation.
The square law equation. So the square law equation, of course, see each of these I1 and I2, you know the square law equations. Okay, so I1 is K prime by 2. So you know these two as well. What else? You have I1, I2, VGS1, VGS2. You need 4 equations. Of course, the fourth equation is this. VID is basically VGS1 minus VGS2. If you apply KVL through this path.
Yes.
Okay.
Yes.
So you now have these equations describing system. So you basically want this VID at which the current, one current becomes 0, other becomes 2 naught. So the way to do this, you can find out, the equation for this system. So you can find out basically IOD as a function of this is what you want. This is what you want. Okay, so this is what we want to extract out from these equations, and indeed it's possible. If you look at Razavi's analog textbook, he has done it. I mean, you can do it yourself, of course.
Yeah.
Of course, you can do it yourself. Okay. And you will find that if the nominal currents are I naught each, you will find that this value VA will be something. Does anybody know what this VA is? Does anybody remember what this VA is?
Root 2 times that VGS VD cell.
Correct. But what is this VD sat? VD sat is basically okay.
Yes, sir.
So you'll find that this is some root 2 times this value. Okay, the nominal VD sat. In reality, this is a large signal operating point, but the nominal VD sat. So if you apply this, the mixer will switch properly. If you don't apply even this much, the mixer will not switch properly. So there is some lost current in the mixer. That's the point. Now imagine you're giving a square wave. Okay, so clock and clock bar. If this amplitude is not root 2 times VGS minus VT, what will happen to the two currents? I am basically passing I0 plus IRF. I expect this to go to I0 plus IRF and 0 and I0 plus IRF. But that won't happen if this amplitude is not enough. Okay, what will happen is that it will go from some finite value to something less than this.
Okay.
So in other words, there will be a common mode value and the differential mode value. The differential mode value will never be equal to I0 plus IRF. Okay, I hope that makes sense.
Yes.
Okay.
Sir, in the same circuit, you have said like in
Yeah, in the same circuit, what have I said? Hello. Are the others able to hear me? I lost that student who asked the question. Are the others
Yes,
able
sir.
to hear me?
Yes, sir. I can hear you.
Okay. Who was the student who had that question?
sir, I got disconnected.
Oh, is this Shravya?
Yes, sir.
Yeah, go ahead, Shravya.
Sir, in the same circuit, you have said the waveform appears at the like it appears like a periodic with TL low by 2 period at the source of the both the top NMOS.
The source, you're talking about this point?
Yes, sir.
And what have I said? What have I said there?
Like when the switching is not ideal,
Uh-huh.
it must be actually a V naught. Like when it is ideal, it is a constant at V naught minus VGS. If V naught is the amplitude of the LO.
Correct.
But when the switching is not ideal, it appears like a periodic of TLO by 2 wave something.
Yeah.
I didn't
So,
understand that wave regarding that. Sir.
yeah. So what will happen is that I think in one of the lectures I have covered the displacement current. Have you seen that lecture?
Yes, sir.
Okay. I think the point that I wanted to make was that if you look at this node, it is expected to be quiet. It is expected to be some DC value at V0 minus VGS 23, correct? Because at any
Sure.
instant, either M2 is on or M3 is on, and each of them has a gate voltage of V0, okay, and it has a current of I0. Okay, so this voltage is expected to be constant flat at this voltage. But in reality, because of displacement currents, why do you have displacement currents? You have some capacitance here, which is CdB1. You have CGS2, and you have CGS3 as well. Because of displacement currents, this voltage will not be quiet, first of all. Okay, having said that, the dominant component at that volt node, what I said was, because it's a common mode voltage, okay, it'll be DC plus even harmonics. Why did I say DC plus even harmonics? Well, the reason is very simple. If you go back to this function, you will find that this function actually has even harmonics. It could have even harmonics as well. Okay. If it has any even harmonics, you will indeed find those even harmonics appearing at this point, because this is the common mode node. Does that make sense?
Okay.
For
But
odd
I
harmonic,
mean,
for odd harmonics, you will analyze it in this fashion. You will apply a delta V here. Okay, because it's a fully differential circuit. If you have even harmonics, there will be common mode signals. They will be appearing equally on both sides. In which case you will get delta V here, and this will be delta V minus VGS, right? You can get the second
yes.
harmonic at this node as well.
Okay.
That was simply the point I'm trying to make. So see, basically these displacement currents will occur every time M2 and M3 gate switch. Okay.
Okay.
So what you will normally get is something that looks like this. You'll get a DC voltage, on top of which every time it switches, so every half period, so T every time it switches, that will happen twice a cycle, you will get a glitch there. Okay, so you may see something like this. Actually, you will see something the other way. I mean, you may see something like this. Okay, it is also possible for you to see something like this, depending on how the displacement current works. All of these are second harmonic contents. Okay.
Okay.
Yeah, but typically you will see this, what is shown here. At every time when it switches, you will see a displacement current, and that will cause the second harmonic content to change there. This will get even worse because CGS2 and CGS3 are not equal when the transistors are switching. This displacement current will get worse. So the second harmonic content at that node will get worse. That was the only point I was trying to make.
Okay.
Okay, and of course that will affect the linearity of the mixer, because M1 could go into triode for a brief period. Okay.
Okay.
Yeah. Any other questions?
Sir, in the in the sampling mixer in pattern mixer, we discussed a double balance would have the same conversion gain. There is no improvement, right, sir?
Correct.
As single balance, same gain.
Right.
Even why is it not for the active mixer, sir? It must be also having the same gain, right?
No. So in the case of the active mixer, you are basically adding currents, not voltages, at high impedance nodes. You will not see that effect. You are basically in the case of the active mix. In the case of the passive mixer, you have switches, and for some period of the time, the input can be transparent to the output. That will not happen in the case of active mixers. So if you take active mixers, what if you try to combine single balance versus double balanced? What is coming out is a current, first of all. not a voltage, right?
Yes, sir.
So you will not see that effect because first of all, the so I1, I2, I3, I4. So first of all, what is the impedance looking downwards here? It's very high, right? So basically at that point, so let us say at any instant, so this is M1, M2 and M3. At any instant, M2 is either off or in saturation, correct?
Yes,
When
sir.
it's off, the impedance is high. When it is on, M2 is acting as a cascode for M1. So this impedance is indeed high at every point. So it is simply like adding currents, isn't it?
Yes, sir.
So I1, I3. So this is basically IO plus, let us say. Okay. The similar is not the case in the case of the passive mixer. Okay, when the device is on, it's a switch, right? It's basically in the deep in the triode region. You don't see that effect at all. Does this make sense?
In like I refer to the Rajavi textbook, they have for the passive mixer actually in the sampling mixer, they said like they have given an example that the as differential input is being applied and it would be 2V naught in that case. So the gain is not changing in that they gave an explanation like that.
The gain is not changing. What does that mean?
Like
I will check
uh,
it. So I will check it and get back to you, Shravya. So can you just email me
oh,
the section after this today's
oh,
class?
okay,
I will
sir.
check it and get
Okay,
back to you.
okay.
Hmm? Yeah,
Like I'm saying that for the sample mixer, sir, not this one.
I
Like
understand.
for the sampling mixer, they solved as an example the double balance mixer gain.
I see.
Mm.
I
So
will
that
take a look
they
at that.
gave that reason. Okay,
I
sir.
understand. I'll take a look at that and then I'll see. Okay.
Mhm. Sir, in the passive mixers noise analysis,
Uh-huh.
uh, I didn't understand the correlation part, sir. Like for the sampling passive mixer, uh, from the correlation part, I didn't understand the derivation. Like how did you calculate the noise power,
Okay.
not voltage?
Okay. So I will have to have a separate class to discuss that as well. Okay. So I'll probably do that separately as well. Just like maybe in the same class that I deal with the active mixer noise, I'll also do that as well. Okay. Probably I can't do that today, but I'll do it in a separate class.
Okay.
Because that's going to be quite long. If I start that this thing derivation, it's going to be a full class. That's why.
Okay.
Same with noise of the LO devices in the active mixer.
Hello, sir.
Yes.
Sir, in that passive mixture noise calculation, we have taken a approximation from 0 to FLO by 10. In that small frequency range, that noise would be common in both the outputs when the in both outputs, right, sir? While
Okay.
from
Yeah.
switching from the hold to tracking mode and tracking to holding mode.
Yeah.
So I am understood it for the while tracking to while switching from hold to track mode because discharging will be fast, but still it will be not fast so that the at lower frequency noise get discharged. But I didn't understand the opposite one. Like while switching from tracking to hold mode, while that noise from that section get comment both. That is why it is in correlated portion, right? I didn't understand that one.
Actually, just 1 minute. I am not sure I understood fully. Just 1 minute. Give me a minute. Let me try to uh, give me a second. I'll pull up that lecture and I can. Do you remember the lecture number?
Uh, it is week 8, I think. I think week 9 first lecture, I think.
Okay, give me a minute. Hmm. Is it this lecture? Sovan, is it this lecture?
Sir, can you scroll down a bit?
Yeah.
No, sir. I think the after this one. After this
After
one,
this
sir.
one. Okay, just give me a minute. No, the next one deals with the input impedance.
Sir, the very last lecture of this mixture series, sir.
The very last lecture of the mixer series. 1 minute. So let me see if. Ah. Just 1 minute. Very last lecture of. Okay. I'll share something. You tell me if this is the one. Is it this one?
So can you scroll down a bit?
Yeah.
No, sir. My laptop is not working. That's why I cannot tell you the.
Okay.
OS.
So when you do one thing, after today's class, you just tell me the lecture number and the specific point. I'll look at it and then I'll get back to you.
Okay.
Okay.
Okay, sir. Okay,
Yeah,
sir.
I'll look at it and get back to you. Okay. Any other
And sir, can you
questions?
explain the flicker noise, that up conversion of the flicker noise while in the when if there is an in there's a part where you explain that the flicker noise might get up converted into the RF band. So that part can you explain a bit, sir?
Just 1 minute then. Okay, just one. Let me look at. Okay, I'm going to present something. You tell me if this is the one that you're talking about, so that it'll be easy for me to. Is it this portion?
Yes, sir. The from beginning of this lecture only, sir. Yes, yes, sir.
Here, noise from the GM stage.
Yes. No, sir. One by f noise, sir.
Yeah, this portion. So this portion, right?
Yes, yes, sir. Yes,
Okay.
sir.
So you're talking about this portion. So see the circuit basically has 1 over f noise around DC, right? So
Yes, sir.
imagine what would happen if you didn't give any RF signal. What would happen? What will be the output? I take a mixer. I give no input to the transconductor. I only look at the output. What will I get?
I mean, only the omega L and 3 omega L, this portion, these frequency components will be there, sir.
These
That
frequency component will be there.
RF bands will not be there.
Okay. So basically what will happen is that you'll have some bias current, right? So the bias current will go from 0 to maximum. Okay, so if I were to so if I take a mixer, okay, and I'm giving at omega LO, but I'm giving only DC. Normally I would give DC plus omega RF. I'm giving only DC. Okay. What would happen is that if I look at the output, so go back, so to my mixer, I'm giving only IDC here. What will I look at? What will I get at the outputs? I'll basically get a switching waveform. When M2 is on, when the clock is high, when the yellow clock is high, M2 will be high. I'll get IDC flowing through the output. Otherwise, I'll get 0. Same thing for the other side, right?
Okay, sir.
What I'll get at the output is basically it'll go between 0 and IDC. So if I take the fully differential output, right? In fact, for the fully differential output, it will go from minus IDC to plus IDC, correct? I'll not even get a DC
Yes, sir.
component. So differential. So if you look at this here, if you look at the frequency components, of course, as you pointed out, I'll basically get omega LO, 3 omega LO, 5 omega LO, etc. Correct? This is what I'll get
Yes.
at the output. Is this okay?
Yes, sir.
Now, if I give a very, very small baseband signal, I'll give DC. So just give me a minute. So what I'm going to do, I'm going to give a small baseband frequency. What will happen? One tone at baseband.
I mean,
What will I get at the output?
we will have a frequency component at omega L minus WBB. Omega, I mean, base band.
I'll get these, correct?
Yes.
Okay. So now imagine what I'm giving is basically DC, okay, plus some flicker noise. So there is some VDC plus flicker noise. What will you get at the output?
Flicker noise about each W omega L, 3 W
So
omega
you'll
L, 5
basically
W
get the
omega L.
flicker noise skirts around each one of these, right?
Okay. Okay.
That's all. So this is purely mixing action. Whatever you have on the transconductor side will get upconverted around DC.
Okay, sir.
Okay, so if you have flicker noise, 1 over f noise will get upconverted, just like if you had DC, you will get a tone. If you had any frequency around DC, will get upconverted as well. Flicker noise will get, sidebands will also get upconverted. So any flicker
Okay.
noise in the baseband device will go around LO. If it's a transmit mixer, it's a problem. If it's a receive mixer, it's not so big a problem. Right?
Okay, sir.
Because you are interested in, depends on what you are interested in at the output of the mixer. If you're interested in baseband, you don't care, right? At what happens at omega LO, 3 omega LO, etc. You're going to filter it out very strongly.
Okay, sir. Yes.
Yeah. Okay. Any other questions? Okay, so this is what I'm going to do. What I'm going to do is I'm going to have one more class, most likely next week, where I explain noise in active mixers and in general noise, how to handle noise in these types of switching systems, specifically noise of the switching device. I think the other stuff is easy to handle, noise of the switching device. Similarly, passive mixers on, I think, specific points. There was a question about the noise in the passive mixer. I'll handle that as well, right? So those two things I'll handle in another, maybe one class next week. Okay. And Shravya, you please send me the portion that you are talking about. Sovan, you please send me the, the portion of the lecture that you were talking about.
Okay, sir.
Okay, sir.
I'll discuss with you both separately.
Okay, sir.
Okay, sounds good. Anything
So,
else? Otherwise,
so
we'll end the class today. Yeah, go ahead.
the Tannis, multi-Tannis circuit, can you explain it, sir? For us?
Yeah. Where is the 1 minute? So, do you remember the lecture number?
It is the third lecture of the mixture lecture series, sir.
I see, third lecture of the mixer series. Okay. Yeah, I think I found it. This is the one. Yeah, I think
Yes,
that's
sir.
the one. Okay. So, see, the if you take a actually, you remember the differential pair that I was just talking about, IOD versus VID. This multi-tannet circuit, the basic idea is the same. Okay, so the basic idea is that if you, in fact, this thing will not give you a tan H. It is generally called a multi-tan H because if you implement it with bipolar transistors, the IOD versus VID will have a tan hyperbolic characteristic. For a MOSFET, it will not have that. It will have some square root type of behavior. Okay, now the point is you can bias that characteristic, just like we saw that IOD versus VID passes through the origin. But it is possible to move that characteristic to the left or to the right. Okay, by changing the size of the device as well as the bias voltage at the gate of the device. It is possible to change that. So imagine you are able to change the current flowing through one of them compared to the other. Okay, the voltage VID at which the differential current will be zero will be positive or negative. Does that make sense? Take a differential pair.
Okay, sir.
Normally, if they had the same common mode voltage at the gate, two gates, the bias current will each be half of the DC current, current source.
Yes, sir.
If you change the gate bias voltage for one of them, what will happen is that one of them, instead of having imagine that current source is 2 I naught, right? Instead of having I naught in each one of them, you will basically get maybe, I don't know, I naught by 2 and 3 I naught by 2 is possible, right? The minute you do this, the VID at which current becomes 0 can either be made positive or negative, right?
Okay,
It is also
sir.
possible to do that. Instead of changing the DC voltage, you can also change the size of the device. You can do that in either way.
Okay, sir.
I don't know if you're able to get the full import of what I'm saying.
Yes, sir.
I'll draw it.
Yes, sir.
I'll draw it so that it will be completely clear. I have a current 2 I naught. So I have V1, I have V2. Okay. V1 minus V2 is VID. And this current is IOD. I am plotting IOD versus VID. Okay. Now, if I had equal W over L's, what will happen? This curve will look something like this, right? It will pass through the origin. It will pass through the origin. But imagine, so in that case, at the bias point will be such that I have I naught and I naught. But suppose I take a case where W over L2, so I have W over L1 and I have K times W over L1, where K is greater than 1. What will happen to this curve? Will I still have currents of I naught and I naught?
No, sir.
You won't.
In I2, in the second branch, the current will be more than that of the first branch.
Correct. So this will be larger current than this. So this current I1 will be less than I2. Okay. So imagine M1 and M2. So the VID for which the two currents will be equal, where IOD will be 0. IOD will be 0 when the two currents are equal. Okay. That will happen at a positive voltage. You have to apply a slightly larger voltage at V1 compared to V2 to equalize the currents. Correct?
Yes, sir.
And if you apply VID, I1 will be smaller than I2 so that IOD will be 0. You get something like this. Okay. Similarly,
Yes, sir.
if you made it W over L2 and K times W over L2, K greater than 1, the reverse will happen. Get a curve like this. Right? You'll get three sets of characteristics. Now imagine you take three of these guys. You can add the currents. It's a high impedance nodes. These are all will act as good, current sources, right? If you add three currents where you have three of these, you will get a fairly broad curve. Imagine you're adding all of these characteristics together by adding the output currents for the same VID. Imagine you're plotting GM as a function of VID. What is GM as a function of VID? Well, when the two currents are equal, you will get maximum GM, which is GM1, and then it will start falling off. You can see that the slope of that curve is falling off. You get something like this, right? For the blue curve, the maximum slope will occur here somewhere. Right? For the red curve,
Yes,
the
sir.
maximum slope will occur here. If you add the currents, you are effectively adding the GMs. So the resultant, you can get a fairly flat GM. So in other words, the dynamic range, the GM flatness will occur over a larger range of VID. That will of course give you better linearity. Okay.
Yes,
In other words, you can apply larger VID for which the circuit will still give you GM. That is what is linearity, right? In one sense. Okay.
yes, sir.
Yeah. So this is what the basic principle is of the multi-tangent circuit. This I have shown you for a for a MOSFET. You can do it for a BJT as well. The exact equations will change. The large signal equations are different. It happens to give you a tan hyperbolic. Okay.
Okay, sir.
That's all there is to it. Okay. Any other questions? Okay. If there's nothing else, then we'll close for today.
Thank you, sir.
Okay. Thank you.